So, needless to say, we haven't posted the groups yet, and I'll tell you why when we get to Administrivia. We had a little bit of trouble. It appears that everybody wanted one particular section, so we had that's probably good. We had a third of the class in that particular section, so I'll tell you about it in a sec. Okay, settle down. So, last time we talked briefly about a history of operating systems, and I don't know, you may ask the question, why bother? But it's always kind of interesting, I think, to find out how technology and needs kind of influence where we are now. And you could ask yourself, what about the things that I talked about last time led us to Vista? I don't know. Or Linux, all right? That one's maybe a little better. And we mentioned that there were a bunch of distinct phases, all right? There's sort of this one phase where hardware was so expensive that humans were considered bootloaders, basically. It's like, let's hire a guy to wire a program up. And then we kind of got through this point where hardware was a bit cheaper, humans were more expensive, and so they started thinking about graphical user interfaces and how to make things easier for humans. And then finally, today, hardware is really cheap. Humans are really expensive, and the trick is sort of how to make use of hardware to make humans' life better. Okay, that's kind of where we are now. I don't know what's going to be next. You know, I don't know, some form of cyberspace with, you know, accesses embedded in your brain or something. I don't know. Could be no difference between humans and computers. I've often thought that. No, I'm just kidding. So rapid change in hardware has led to changing in OS, right? So we went from batch to multi-programming to time-sharing to graphical user interfaces to ubiquitous devices to cyberspace. I don't know, we're kind of there now. And we've also seen a gradual migration of features from big machines into small ones. And today is kind of a funny situation. Once again, we've got lots of little devices. Or not once again, we have lots of little devices, but the complexity of the operating systems running on these little devices reminds us a bit of the 60s when things got so complicated. It took 6 years to make a working operating system, and it still didn't work. Okay? I think we're in that mode right now, and there's a good question of what to do about this. The way we got out of it before was people went in and ripped out a whole bunch of functionality. I don't know. Are we willing to do that today? Hard to say. So this was just another quick look. We sort of showed all of these ideas from the mainframes. Multics is sort of the project of the original complexity point, have all found their way down into little handhelds. And arguably will keep going into little embedded operating systems. Okay, how many people have either heard of or played with TinyOS? Okay, so, you know, the interesting thing is TinyOS was a project that was developed here at Berkeley to deal with little tiny sensors that are, in theory, everywhere. Okay, and they're actually using these sensors in wildlife refuges to monitor birds, and they're using them to monitor earthquake zones and everything. What's interesting was they needed an operating system, so they designed one. They called TinyOS. And yes, indeed, these little tiny devices that are in trees and whatever are all running operating systems. So it seems like a topic that keeps coming up. So we briefly breezed through some of the implementation issues, and the reason we did that was basically because we're going to talk a lot more about this as time goes on. But the one thing that sort of the duality here of policy versus mechanism I'm going to want to keep bringing up. So policy is what do we want to do, and the mechanism is the how, or the actual pieces underneath that are used in support of the policy. And it should be separated because policies often change. Okay, and we're going to actually talk, so the first policy we talked about was one in which two processes that happen to be running on the same machine could not touch the other's memory, right? That was totally isolated. We're going to change that today. We're going to punch a little bit of a hole in that policy and allow them to communicate on restricted pages. Okay, so the policies change, the mechanism of the address translation doesn't. We didn't talk much about this, but as you will learn playing with nachos, there are many algorithms that come into play in all parts of the operating system, and if you use a linear algorithm on something that you search a lot, you're going to start noticing that, right? So the algorithmic stuff that you may have learned in CS70 or 170 certainly comes into play in the operating systems. We briefly mentioned this notion of threads. We're going to talk about threading a lot in the next few weeks, and then we're also going to mention event-driven models such as show up in graphical user interfaces. There's issues of backward compatibility, which we've also glossed over. Basically, one of the reasons that Windows has some of the complexity it has is that Microsoft intended to continue to run programs that worked decades ago. And that made them, put in some very complex pieces. I was just talking with some Intel engineers about an up-and-coming new processor that's intended for the graphics market. And what's interesting about that was they still have real mode, which is something that showed up in the 8080 processor. Okay, so backward compatibility shows up a lot. Okay, so what's our goals for today? So we want to actually target this notion of multi-programming and multi-processing, and we're going to specifically look at something called multi-threading. So there'll be a lot of different multis that float around today. We're going to try to learn what a process actually is. There's sort of be the things you think it is, what a process you think is, and we'll find out what we view them as. And we'll sort of see how processes are related to threads and address spaces. So let's start with this notion of concurrency, which is, again, this multiple things happening at once. And what's a thread of execution? Okay, so one view of a thread of execution is it's an independent fetch, decode, execute loop. So you all remember from 61C, right, how basic processor works. We're going to review a little bit of that in a couple of slides. But basically, a thread of control is, a piece of a serial execution that's busy doing its own thing. And we can have more than one of these going on simultaneously. That gives us multi-threading. Okay, and it's going to be operating in some address space for protection. We'll talk a lot more about that. This notion of uniprogramming is that there's only one thread at a time. Okay, very old school. MS-DOS, early Macintosh, batch processing systems. Very easy for the operating system designer because they only have to worry about one program going on at once. Not very convenient for either the programmer or the users. Okay, when was the last time you used a system that could only do one thing at once? Okay, like what? The iPhone. Come on, the iPhone is cool, right? Yeah, I guess the operating system that Apple puts on the phone has a tendency to mostly run only one thing at once, although it can still take interrupts and pull in email and so on. So it's not quite doing one thing at once, if you were to look under the covers. I bet that there's been it's been a long time since you guys accessed a computing device that did only one thing at once. Certainly doesn't make sense for our view of personal computers today, right? Because you sit down, you've got, you got Microsoft Word, you got a browser, you've got Excel, you've got some window you're programming in, you're compiling, who knows what. There's a lot of things going on at once. Multi-programming is more than one thread at a time. And of course, this was originally showed up in Multics, and it's in all the IXes, Unix, Linux, et cetera, OS2, Windows NT, 2000 XP, Vista, Mac OS. Often called multitasking, but that gets a little tricky. And many-core, which we've mentioned a couple of times, sort of implies multi-programming, right? I don't know. Does it? Yes. Oh, okay. Hold that thought. Does many-core imply multi-programming? Yes. Go ahead. Okay. I didn't actually. So